Hello, this is section 4.7. We are doing optimization problems. These are word problems, and they're actually not super hard if you kind of get your procedure down. So basically it's writing a couple of equations and taking the derivative. So all stuff that you've done before. So don't panic. You know, I know word problems are sometimes hard for people. They are hard for me. I do struggle often with those, and I have in my math career. But if I can do them, you can do them. So here's your procedure. You want to kind of write this down. It gives you a little guide for how to do it. And as you are doing these problems, try to memorize the process. So try to do it without looking, and get yourself used to the process so you have that memorized. You have to have a game plan in order to play the game. So here's our first example. You have 100 feet of fencing. You want to fence 3 sides of a pasture. What is the largest possible area? So first thing that you want to do is draw a picture. Okay, so there's something over here that's not being fenced, and then the rest of the pasture. Oh, that's fun. Is being fenced, and you want to label the parts of your picture with variables. You can choose what they are. Try to minimize how many variables you use, because the more you use, the more you're going to have to substitute out. So typically you can get away with labeling most of these with 1 or 2 variables. The second step is to write an equation for what is being maximized or minimized. So I skate through this problem and I look for the sentence that says largest, maximum, minimum, smallest, and I look at what we're talking about, and that's going to dictate the formula that I write. So in this case, I'm going to go area equals x times y. That's how you find the area of a rectangle. And then the next step is write another equation that relates to the 2 variables in number 2. Often it's involved in the number that's given in the problem. Sometimes it's not, and you have to kind of figure it out from the picture, but that's a clue. So I have 100 feet of fencing, and then I have to say, well, what is that doing in the problem? And the answer is that it's measuring a perimeter. Okay, so my second equation, this is my second part. My third part is to write my second equation. It's going to be by perimeter. Now in this case, it's not all sides, it's only 3. So I've got x plus y. And that's going to be my other equation, and I know the perimeter has to be 100, so here we go. Okay, and these 2 equations should be in terms of the same letters. You shouldn't be introducing new letters into your equation number 3. There. Fourth step is to sub number 3 equation into number 2. So we're going to solve this for a letter. It doesn't matter which one you do. When I'm using x and y's, a lot of times I'll solve for y just because then it puts the function in terms of x, and that seems more normal. But you can solve for either one. Whoops. So I'm going to subtract over the 2x. And then you're going to take that and substitute it in. What the idea is, we're trying to get our equation that we want to maximize in terms of 1 variable instead of 2. So I have x times 100 minus 2x. And then you take a look at the domain. This domain, you can do this as step 5, or you can put it after the next one. It doesn't really matter. In general, we just want to know what can x run from, and we're interested in x because that's what we're in terms of. So x has to be bigger than 0, right? I mean, you can't have a negative length. Okay, and then often you can find the maximum for x by saying, what if the other variable is small, like 0? So y's smallest is 0 too, right? It has to be positive, has to be greater than 0. So if y was 0, what would x be? And the answer is you'd come up here to take a look at how they're related. If y is 0, then I get 100 equals 2x. So that means the x is maxed out at 50. Now, it can't actually be 50 because y is not exactly 0. Like, you can't have a 0 length. But that gives you your cap. So x is going to be somewhere between 0 and 50. This is important for a couple reasons. Sometimes these restrictions are or equal to, in which case you need to test your endpoints for extreme values. And the other reason is sometimes you'll get more than one critical point, and this this restriction right here will help you pick which one's the correct one. Okay, so that's our step 5 here, I guess. Okay, and then step 6 is to find the min or the max of your function. So that's going to be just like section 4.5, finding min and max. So we start by taking the derivative. Actually, before I do that, I don't want to do the product rule, so I'm going to multiply this out first. 100x minus 2x squared, and now I'm going to take the derivative. So dA dx equals 100 minus 4x, and then I'm going to set that equal to 0 to find my critical point. So x is going to be 25. Okay, I take a little peek at my domain, make sure I'm good, that I'm in that range there, and then I'm going to make my sign chart, figure out if this is a max or a min. Because in theory, you know, there might not be a largest area. I mean, it might be a minimum area, or there might not be any critical point. The extreme value theorem says that you have to be on a closed interval to find a min or a max, and we're not, so it's not guaranteed that there will be one. So I take 25, put it on my number line. I'm going to pick some test points here. Let's say 5, and because I'm testing rate of change, I'm plugging into the derivative, so I'm plugging this value in here, and I'm going to get positive values on the left, and when I plug in a number like 30, that's going to make them negative. So this function is going up, and then it is going down, so that means this is a max, which is good. That's what we're looking for, is a maximum. So there's a maximum at 25. Okay, and then the last step is to go back and read the problem. This is so important. So many times people go through this whole process, get all the work done, and then they don't answer the question, which is a bummer. What is the largest area? So they're not asking what's the largest x value, which is what this is. They're actually asking what's the largest area. So largest area, well, the area function is x times y. And so in order to plug these values in to find the area, I know what x is, but I need to know what y is. And oftentimes this second equation up here in step number 3 is what relates your x and your y, or your two variables, whatever they are. So that will help you find your corresponding y value. Okay, and y is going to be 50. That was a pretty simple example, and a lot of times you can eyeball these and guess at it. I would encourage you not to do that on the simple problems. Get used to the process because they're not all simple. Okay, so this ends up being 1,250. Did I put a label on here? Yeah, feet. So area is going to be feet squared. Area is always a squared label. Volume is always a cubed label. Length is always just the label without a power. All right, so that's how you do these problems. Let's take a look at one that's a little bit, maybe a little more challenging. So we've got a rectangle box with a square base and an open top. The volume must be 216 inches cubed. what should the dimensions be to minimize the surface area? And then second question, what is the minimum surface area? All right. So first step, we're going to draw a picture. So I've got a rectangular box. That means its height is a different size than its base. So let's do this. Rectangle. That's nice. Sorry. Let me try again. Rectangle. Okay, there we go. Here we go. All right, and I'm going to call the height y, and I'm going to call the bases x. Notice that it's a square base, so I don't want to put a z in there because I want to minimize the amount of variables that I use. So x, x, and y. My first thing is to talk about what do I want to minimize or maximize. I want to minimize the surface area. So I need to figure out what the surface area is. I'm going to call that S, surface area. And the way you find surface area of any object is just you add up the areas of each side. So this box has 4 sides that are like this one all the way around, and the area of all of those is x times y, base times height. So I've got 4 of those, okay, and then I've got one bottom. The bottom is this part right here, and that's base times height as well, which is x times x, which is x squared. There's no top on this, okay? Otherwise, if there was a top, this would be 2x squared. So that's my surface area. This is the pink part, the 4 sides there, and then the blue. And the next step is to get, oh, I guess this was the first step. This is the second. What's another equation that relates these things together? And again, oftentimes it's associated with your extra number. Look, the other thing mentioned here is volume. So let's write an equation for volume of a cube. It's base times height times width. That's how you find volume. So since the volume has to be 216, that's going to be this. Okay. And I'm going to solve this for one of my variables. Again, I'm going to choose y, not this time, not just because I want it to be in terms of x, but because if I choose x, I have to square root both sides. And I want to stay away from square roots. So kind of choose wisely when you're picking which one to solve for. So y equals 216 over x squared. And then that's what I'm going to take and plug in here to the surface area. So surface area equals 4x times 216 over x squared. These x's cancel, and I get 216 times 4. Oh, sorry, I missed the x squared. I shouldn't have done that in color. I missed that. Okay. These x's cancel, and so I get 864 over x plus x squared. All right. Now, domain is, let's just check that. Domain x has to be greater than 0, right? Okay. If y was 0, let's look right here. Let's see. Let's look at this equation. 216 equals x squared y. If y was 0, that would 0 this guy out. So that would also be a volume of 0. So I don't know. I can't easily look at what offhand the dimensions cap is. So this probably could run up as big as I want, as long as the volume is constrained. It may not be important, okay? What is important is that x can't be 0, because I'm looking at this, and that means that 0 is not involved. Obviously, it can't be 0 because you can't have, that would give you 0 volume. All right, so we're just kind of paying attention to the problems parts. This isn't like super critical in your computation, as long as you just keep your head on and don't pick like a negative number or something, okay? So we took a look at the domain, and now let's maximize the function. So here we are. And I'm going to take the derivative. So ds dx is going to be negative 864 x to the negative 2 plus 2x. So and that's what we get here. And I'm setting this equal to 0 to find my max value or min value. So I'm going to subtract or add over this 864. Just make everything positive. And I'm going to cross multiply here. Okay. So I get 2x cubed equals 864. Divide by 2. And then cube root both sides. All right, and if I reduce that, that's going to be 6, the cube root of 2. Okay. All right, sign chart. Let's take a look. 6 times the cube root of 2 is definitely in our realm of possibility with the domain. And this, if you do this out on the calculator, this is about 7.56. That's valuable. I do not want decimals on your answers, okay? But it's helpful to know a decimal so that you can pick your test points and make sure you're picking something on either side. So, like, I'm going to pick 1. We'll go and plug it up into here, and you end up getting negative values here when you plug in 1. And then if I choose like 10 over here and plug that in, I get positive values. Okay, the positive 2x takes over the fraction when you get bigger like that. So this function is going down and then it's going up. So what that means is this is going to be a minimum, which, good news, that's what they're asking for. Okay, we want to minimize the surface area. Why would you want to do that? Because when you're constructing a box, you want to minimize the cost of the box. So you want to maximize the volume and minimize the cost of the surface area. All right, now last step is read the problem. First question, there's 2 questions. What are the dimensions of the box? So my first answer is, well, the x dimension is 6 times the cube root of 2, right? And my second dimension I get by plugging that value in to my equation that relates x and y. Okay, and so I get 216 over 6 times the cube root of 2, and that's squared. There you go. Okay, let's distribute in, clean this up a little bit. It'll make our life easier later. This is going to be 36. That squares, and then the cube root, the 2 squares also and makes it a 4. And I don't know if you went over this in pre-calculus, but oh well, let's reduce first. This is 6 over the cube root of 4. It's helpful to know how to rationalize a denominator when you've got a higher root, because sometimes that makes it a little more simple and we can get rid of the fractions. So what I have here is, on the bottom, is I have the cube root of 2 squared. If I can make that 2 cubed, then the cube will cancel with the cube root. So the way you do this is you multiply by the cube root of an extra 2, okay, on the top and the bottom. So now I've got the cube root of 2, and downstairs I've got the cube root now of 4 times 2, which is 8, which is 2 cubed, and these guys cancel. So this is going to be 6 cube root of 2 over 2. And now that reduces to 3 cube root of 2. Okay. I think I made a mistake. 2. Well, if I did, you can catch me on it. No, I think that's right. That's right. Okay, good. Just want to make sure. So these are the dimensions, all right? The second question that it's asking is, what is the surface area? And the reason that I went through this effort to reduce the y is because I knew I was going to have to do the surface area, which is kind of a monster. So I wanted to make it as simple as possible. In general, this value right here is a fine place to end. And if you want to mess with that fraction, that's fine. You can plug that value in. It's just easier if you get the fraction out of there. So this becomes 2 squared, that's your x squared, and then 4x y. Okay, so this is going to be 36 times the cube root of 4 plus 72 times the cube root of 4. And then again, this is all multiplication division. So multiplication powers just distribute in. Unlike roots combine. In addition and subtraction, they don't. They have to be exactly the same. So cube root of 4, cube root of 4, that takes the place of your variable. You add just like you would x's. This ends up being 108 times the cube root of 4 inches squared because it's surface area. Okay. All right. They'll practice with some little throwback to Algebra 2 with all the roots. If you want to try one now, you should try example 4.33. I'm going to do another example here, maybe one more. Okay. A rectangle is inscribed in the ellipse x squared over 4 plus y squared equals 1. What dimensions of the rectangle maximize the area? All right, so remember from Algebra 2, this is actually a graph of an ellipse. Well, it tells you that, but also the way that you graph it is it's centered at 0, 0. We know that because there's nothing in here with the x and the y. And the square root of this number is how far you go on the x-axis out. So I'm going to call this -2 and 2. And then the square root of the number down here is 1. So that's how far you go on the y-axis. So it looks like this. Okay? Only it's like, pretend like that hit the marks right on, okay? That's your ellipse. And then you've got a rectangle that's inscribed in it. What that means is the corners touch and it's on the inside. Okay, I'm going to try to get that to happen here in my picture. Here we go. Okay. And we need some variables, some dimensions, and the dimensions actually in this problem, it's a little bit different because one of my formulas is already given. Okay, so that eliminates either my step 2 or 3, depending on what equation they give. And they've already defined my variables as x and y, which makes sense because we're on an x and a y axis. So I need to define the dimensions of this rectangle in terms of x and y. And the easiest way to do this if you're centered at 0, 0 is to call this distance right here x and this distance right here y. Makes sense. So this point is x comma y. Now be careful with this because that is, let me do this in a different color so you can see. This is x and this is y. So I want to maximize the area of the rectangle. Area of a rectangle is base times height, right? Which is not x times y, because x is only half of the width of the rectangle. So the whole width is going to be 2x. And the height, half of the height is y, so the whole height is going to be 2y. Now, you can choose to label this differently, but then that's going to affect this equation. So how you choose to label one doesn't matter. You can do it however you want as long as you're consistent in both of your equations. All right, so here we go. This is my maximizing equation. Now I'm going to take the one, this is my already done step 3. X squared over 4, y squared equals 1. I'm going to solve this for something and plug it in. So let's subtract over that fraction. And y equals plus or minus the square root of 1 minus x squared over 4. Now, what's the domain of this going to be? Well, we're going to say that y has to be greater than 0, okay? And x has to be greater than 0 also. Now, what if y is 1? Look at where this caps out. The ellipse is actually bordered on the x-axis between -2 and 2, and the y values are bordered on the ellipse between -1 and 1. This rectangle can't extend out beyond the ellipse, and the ellipse is bound on the x-axis and the y-axis. So that actually gives us our bounds for our x and our y. The y is not as important, the x is, okay? Now, it's not 4 because x we defined from the center out. So we're just saying, hey, that has to be, that can be 0 or your square or your rectangle collapses, and then that whole distance can only be as far as half the ellipse. Okay, so obviously it's positive though. That's what I wanted you to get at. So when you get this plus or minus on the root, you can just go ahead and choose the positive one. That's where the domain helps you. Okay, so that's my y value, and I'm going to take that and plug it in here. So area is 2x times 2 times this root. So that's going to be 4x times the root, and we need to take the derivative. So this is a product rule and a chain rule. So the derivative is a little bit extensive. So dA dx is going to be the derivative of the first term times the second term plus the derivative of the second term times the first term. All right, first term derivative is 4. And the derivative of this is a chain rule. The derivative of the outside function, okay, that's how the root works. It's a 1/2 power, bring it down, drop by 1, evaluated at the inside function, times the derivative of the inside function. Okay, and then I'm dropping my 4x down as well. All right, so what this ends up being, 4 root 1 minus x squared plus 1/2 1 minus x squared over 4 to the -1/2. And then the derivative of this right here is going to be negative 1/2 x, okay, times 4x. All right, let's clean this up a little. This, and this all multiply together. And I'm left with, oh, that's a minus. X squared, 1 minus x squared over 4 to the negative 1/2. Now, I've showed you this. I'm going to change this root just so we're all on the same page. Change this to a 1/2 power. I've showed you this trick before. It works all the time. It's really a powerful trick. You've got two terms right here, and you've got fraction exponents. The deal is you pull out this to the smallest power, and the smallest power is negative 1/2. So I want to factor out 1 minus x squared over 4 to the negative 1/2. And what that leaves me with in this term is a 4, okay? And what power of this do I want here so that it adds to 1/2 to give me negative 1/2 to give me positive 1/2? And the answer is 1. And it often works out that way. It will always be a whole number, and often it's 1. So again, 1 plus negative 1/2 is 1/2. I'm looking at multiplication in reverse to figure out what that power should be. Okay, if you still have trouble with that, let me know. I want to help with that. This trick is really powerful. And then in this second term, I pulled out this term, so all I'm left with is the minus x squared. And what that does for me is it leaves me with a simple multiplication problem without roots on the inside here. Okay, now it's factored, so when we set it equal to 0, we're ready to go. You just set each quantity equal to 0 and solve. So I'm going to add this over, cross multiply, so x equals plus or minus 2, and over here x squared equals 2, so x equals plus or minus root 2. Now let's look at the domain again. X has to be between 0 and 2. So that's going to opt out those situations that the 2 value here is going to collapse the rectangle. And it's also going to opt out this negative on this root. So my only critical value left that's in the domain is a root 2, which is about 1.4. Okay, and I'm going to pick some test points. Over here, I'm going to pick point like 0.5, say. Okay, and I'm plugging that into the derivative right here, and I get positive values. And then over here, I'll pick like a 1.5. Again, keeping in the domain. Don't test outside of your intervals. There's cutoff points here at 2 and at 0, so make sure you stay inside of those. And if I plug 1.5 in up here, I get a positive value times a negative is a negative. Okay, so this function is going up and then going down, which means this is a max. Okay, we are looking for a maximum, so that's good news. That means that works. And last step is read the question. Question says, what is the max area? So don't tell me the answer is x equals root 2. We got to take our function, which is x squared over 4 plus y squared equals 1, and we need to plug in our x value to figure out what y is. So root 2 squared is 2. That's 2/4, which is 1/2. So y squared equals 1/2. So that means y is going to be plus or minus the square root of 1/2, which is plus or minus 1 over root 2. And the negative, again, is outside the domain for y. So that means that we're just going to choose the positive value for y. So we've got our x and y, and we can figure out what the area is. Now remember, area is not x times y. It's 2x times 2y. Go to the beginning and look at that again. So I get 2 times root 2 and 2 times 1 over root 2. The root 2's and the 1 over root 2 cancel, and I'm left with 4. And go up here, check out a label. Forgot what we're in here. Oh, it's not, it's just XY coordinate system, so that's fine. The area is 4, we'll call it units squared, whatever units we're in. Okay. All right, now the example that I have for you to try here is a cost function, which feels different, but it's the same in that they give you this formula up front. They'll give you a cost formula, and you're just going to take the derivative of that. So it's got a similar feel once you get into it. Here, try example 4.35. Okay. The online homework is kind of the simpler problems. I put an optional book assignment for you to do with some more challenging problems. You do not have to do that, but if you want to step into a little more challenge and just look at some other variations on things, please do that. I find that most people need more practice in this section. So good luck with that, and let me know if